Let's look at this first example. And for this example, I'm deliberately choosing a very simple one where we're in two-dimensional space. And we have our vector function, which is a cosine t, a sine t. And that should easily be seen to represent a curve which is a perfect circle here, centered at the origin of radius a. And we start here when t equals 0, and we go in the counterclockwise direction. I think we've all seen the parameterization from chapter 10 of a unit circle, which would be when a equals 1, or a circle of radius a here, which has this parameterization. I'm just writing it as a vector function. We can compute the velocity vector for this vector function. That's r prime of t. That's just minus a sine t, a cosine t. This will be a vector at any point here that points in the direction. That doesn't really look like it points in the correct direction, so let's fix that. That points in the direction of motion. At any point, it will point in the direction of motion. And the length of the vector, you can compute very easily. The length of v of t, that's our speed function, will just be the square root of this squared, which is a squared sine squared t, plus this squared, which is a squared cosine squared t. And the sine squared t plus cosine squared t is 1, so we'll have a squared under the square root, and that will just be a. I should notice here, I should mention a is a positive number, so that all of this will make sense the way I've said it. So our speed is a. That means this parameterization of motion around the circle is moving at a constant speed, and that speed is exactly a. What are the unit tangent vectors? The unit tangent vectors are just the velocity vector, which is this vector here, minus a sine t, a cosine t, divided by the length, which is a. In other words, that's just the unit tangent vector. The unit tangent vector is just the vector minus sine t, cosine t. The unit tangent vectors will just be vectors tangent to the motion, always of unit length. Now, will those be longer than or shorter than these? That depends what a is. If a is about 2, then you'll see these unit tangent vectors will be half the length of the velocity vectors. How would we then get a hold of this number kappa, the curvature? Well, kappa is defined to be the length of dt ds, which we saw you can compute as the length of dt dt divided by ds dt. And we've already seen that ds dt, that's just the speed, that's a. So that's going to be 1 over a, that's from the ds dt, times the length of dt dt. Well, what is dt, derivative of the unit tangent vector, with respect to the parameter t? We have the unit tangent vectors right here, so that's just going to be the vector minus cosine t and minus sine t, and this has unit length. So the curvature is exactly 1 over a. And this example is very important to understand because it tells us really how this number kappa, the curvature, is measuring how curvy a curve is. If you have a circle of radius a, the curvature is always going to be exactly 1 over a. Which should make sense. The bigger a circle is, the less curvy it is. In fact, if you imagine a really, really, really huge circle, say whose diameter is 20 miles, it feels like you're going almost perfectly straight. You're not, you're curving a little bit, but it's very straight. The curvature is a very small number. Note that the curvature will be exactly 0 when dt dt is 0, and that will happen exactly when you're moving in a straight line. But now if you're going on a tight small circle, let's say you have a small circle like this, the radius a is much smaller, And so the curvature will be much greater. The curvature is just this number 1 over a, which I've already kind of messed up here a bit. So how does that tell us about the curvature of just an arbitrary curve? Well, we could ask at any point, what is the circle that kind of best approximates the curve near that point? And if near this one point, the curve really looks very much like a particular circle, the curvature should be 1 over the radius of that circle. We actually call that circle the osculating circle, the circle that just touches and best approximates the curve at that point. The osculating comes from, I believe, the Latin for kissing, or is it the Greek? I don't know. Anyway, it's the osculating circle. If you look at its radius and take the reciprocal of that, you get the curvature. So you can see here, there'll be a certain curvature. Here, the curve's almost straight, so it would have curvature 0. You can see maybe here, there would be a very big osculating circle at this point where it's almost straight. You could imagine a very big osculating circle there. And maybe here, a very small osculating circle. So the curvature would be much higher at that point. And if you look at any point and see what that osculating circle looks like, take the reciprocal of its radius and you'll get an idea for what the curvature should be. I want to move us up now to a slightly more complicated example. You notice we have the same a cosine t, a sine t as before, but now we're in 3-dimensional space and we have the bt here. I've used this example before, but now we're going to talk a lot more about this example. If we imagine starting when t equals 0, we're here at a comma 0 comma 0 with this vector here for our r of 0. And then as we increase a, just in the x and y coordinates, we go around the origin in the xy plane. But what's happening with the z coordinates? Let's assume here a and b are positive numbers. So as t increases, the z coordinate here will increase and will kind of go around the origin while winding upwards. And that will give us a classic helical shape. Just always going around in the xy plane around the origin, but in the z direction, we're moving upwards at a constant rate, b. We can compute very easily that r prime of t is the vector minus a sine t, a cosine t, and now we have a b in the third coordinate. So what is v of t, our speed function, which is the length of r prime of t? That's just going to be the square root of this squared plus this squared. That's a squared sine squared t plus a squared cosine squared t. Now we have plus b squared. That's just the square root of a squared plus b squared. So this parameterization has us moving around the helix in this direction at a constant speed, but that constant speed is the square root of a squared plus b squared. It depends on both the parameter a and b, both parameters a and b, of course, in this way. What is the unit tangent vector? Well, the unit tangent vector at parameter t is just this velocity vector divided by its length. So it's 1 over, I'll just write 1 over square root of a squared plus b squared times this vector minus a sine t, a cosine t, and b. And at every point along our curve, it will provide us a vector of length 1 in that direction of motion. Notice that that last coordinate is just the constant b divided by the square root of a squared plus b squared, of course. So all of these unit tangent vectors are kind of pointed upwards with the exact same z coordinate, third coordinate, of b over square root of a squared plus b squared. And as far as the x and y coordinates are concerned, they just will have the direction rotating around in a circle with period 2 pi, just because these functions sine and cosine have period 2 pi. When you get to t equals 2 pi, you're back here, and then another 2 pi, and you get back to here, only 2 pi times b higher. Is it going to be easier for us to compute, kappa, written like that, kappa of t, which is the length of dt divided by ds dt. Remember, ds dt is just this, the speed function. So what is, I'll do a separate computation over here. What is the derivative of this unit tangent vector? Well, this is just a constant, so we have 1 over the square root of a squared plus b squared. And then we would take the derivative, we get a minus a cosine t, a sine t, and now we get 0. And so the length of dt is just this constant, 1 over square root of a squared plus b squared times the length of this vector. And the length of this vector is easily seen to be a. And notice we're dividing this by ds dt, which is square root of a squared plus b squared. So when I put in this result from earlier, we get a over square root of a squared plus b squared, again divided by square root of a squared plus b squared, and we get a squared plus b squared. The curvature at any point t is always a constant, and this should make sense kind of by a certain type of symmetry as we're going around at a constant speed. Everywhere the curvature is exactly the same, and the value of that curvature is a over a squared plus b squared. I want you to think about that curvature, and you'll see that it should make sense in a bunch of different ways. If b is 0, then the whole curve just takes place in the plane, and it's exactly like the circle we looked at before. You just go around and around in the xy plane because b is 0, and then the curvature will be a over a squared, which is 1 over a. That's the result we had earlier. What happens if b is very big? Well, what does it mean for b to be very big? If b is very big, I'm going to erase this whole picture here. If b is very big, then as we go around, we're going up very rapidly. And we can just imagine spinning, but going up much more rapidly than the motion around the sides. And what does that do to the curvature? Well, if b is very big, this curvature will tend to 0. And that kind of makes sense. Imagine you have an object in the shape of a helix. You guys are watching this are probably too young for most of you to have had one, but back in the old days, slinkies were very popular. They used to be made out of metal, and they would be in the shape of a helix. And if you stretched it out really far, that would be like increasing this parameter b, and you'd see the curvature, they would be closer and closer to straight. Of course, that would be a problem when you did this to your slinky, because as you stretch them out, they would straighten up, and if you stretch them out too much, they would not want to go back into the regular slinky shape. But what you do is basically force that curvature to get closer and closer to 0 by increasing b. What happens if a is very small? Well, then the curvature will depend heavily on b. If b is small and a is small, you could get all sorts of different values for the curvature. If a is very big and b is small, as we've already said, the curvature will be more like 1 over a, because the b won't contribute much.